Bismillahirrahmanirrahim. Yes, hello everyone, and today we are going to be continuing solving problems from chapter number 6, which is about fires and explosions. And if you just can recall the name of the book, Chemical Process Safety Fundamentals with Applications for Daniel Kroll and Joseph Lover. This is Dr. Bassam Al-Hamid. And what about 619? What it is talking about? So 619, we have an automobile, a car, assembly line. Okay, it says assembly line, okay, for a car. Includes an operation that involves filling the gas tanks with gasoline. Estimate the ventilation rate we have required to reduce the vapors from this operation below the lower flammability limit for gasoline. Why? Because we are filling in some gasoline, and since we are in a closed area, it's a big area of an assembly line, but still it's a closed area, so we need some kind of ventilation rates. Assume that each tank has a volume of 14 gallons for the car, and the tank can be filled within 3 minutes. Okay, so filling in within 3 minutes. So if you want to calculate the RF, you remember the RF, the numbers, how many per minute, if you can recall from chapter number 3. Let's continue. Assume splash filling. If you can recall also from chapter number 3, if we have splash filling, phi is equal to 1, and that's only one tank is filled at a time. Okay, so we'll concentrate on one tank. The molecular weight of gasoline is about 94, and its vapor pressure is 77 degrees Fahrenheit, and at 77 degrees Fahrenheit is 4.6 psi A absolute. Calculate the ventilation air, which is QV, required to reduce the concentration of the gasoline vapor below the TLV/TLWA, the threshold limit value. Now we have two things, right? We can calculate the QV for the threshold limit value, and we can calculate what is the QV to have to be below the LFL, the lower flammability limits. So there are two things here that we can calculate for the QV. So what do I have here? We have 619, and let's start solve 619. So if I'm going to start with gasoline, so I have gasoline, I want to start with the LFL value. And the LFL value, if you go to Appendix B, you can find that it is 1.4%. And here the equations that we're going to be using later, which is equation, which equation it was? It was equation 324. Okay, so I'll say that the equation 324, if you can recall, it is CPPM is equal to Psat into phi. RF is how many per minute, and we have it to VC, the volume, over K QV. K you can recall is between 0.1 and 0.5 into QV into the pressure into 10 to the power 6. So that is CPPM. And since we are calling about CPPM, so here 1.4%, okay, 1.4%, which is a boiling percent. If you multiply this by 10 to the power 6 to just reflect it in ppm, that will be 14,000 ppm. Okay, and where do we get that from? We get this from Appendix B. Appendix B. Great. What about the other threshold limit value that we want? It is equal to 300 ppm. And now we can see that the threshold limit value, and yeah, of course, let me say that you can get this from Appendix G. Now we can already see that the threshold limit value is much lower. Okay, and the flammability limit is 14,000. Which one is higher? The lower flammability limit, which is the gasoline, which is the one which is higher. What does higher mean? That means if I'm going to get a ventilation rate, I want to reduce my concentration, right? I want to reduce my concentration. So just put it here, like this is 300, and well, say this is like 14,000, it's really high. So you're trying to reduce, because of QV, you're trying to reduce the concentration. Going down, till you reach below this limit. I'm happy. Okay, I'm really happy for that. But actually you're exceeding the threshold limit value. So you will need more ventilation to go down and down and down to go beyond the threshold limit value. So you got the idea? So I already can answer that. You need a higher ventilation rate for to work on what? To work on the value of for the threshold limit value. And you already can see here like QV and CPPMs, like there's like an opposite or inverse relationship between QV and CPPM. So in this case, which means that QV, it will be, if you have higher CPPM, you have lower QV. Okay, if you have lower CPPM, you will have higher QV. So lower, higher, or higher and lower. Okay, so we already can get an idea about that. Now, for the sake of calculation, just like do our job here, RF is 1/3 minutes. Okay, VC, it told us that it has 14 gallons, and you just do your math here to convert it to feet cube. So it's 1.87 feet cube. And what else do we have as information? It gave us the saturated pressure actually. So this is, if I can recall the question, just to remember. So we have this vapor pressure is 4.6 psi. So the vapor pressure here is 4.6 psi A absolute. And talking about the atmospheric pressure. So it's 14.7 psi A absolute. What else? So it is a splash filling. So this is equal to 1. I think we have everything there, right? And now once I will substitute with 300, and once I'm going to substitute with 14,000, right? So I'm going to substitute once that or that. So what do I have? What do I have? I'm going to have the answer as following. So QV is going to it's going to be 2,290 feet cube per minute. If I'm talking about the 14,000 ppm, okay. And if I'm targeting the 300 ppm here, my QV value is going to be 6,440 feet cube per minute. And as we said that definitely you need what? You need a higher ventilation rate here, okay, because it's low. You need a higher ventilation rate. Great. So that's the only thing that we have here. I just forgot to say here, we can consider that there's that this is the value of K from 0.1 to 0.5, and because of 0.1 to 0.5, I thought that that was the two different calculations for 314,000 ppm. So actually, the answer here for 300 ppm, just to correct our problem here, our idea is still the same, but just to correct our problem for 300 ppm and 14,000 ppm. So your QV here ranges from 27.6 I think the other way around. So that will be here 27.6 to 138 feet cube per minute. And here for 300 ppm you need a higher ventilation, so that would be 1,290 to 6,440 feet cube per minute. And definitely now the higher ventilation rate is not for that. The higher ventilation rate of course will be for the lower ppm, the higher ventilation rate. Okay, and we already said that ventilation rate. Okay, that was a quick question that was good for to solving 619. The next we are going to solve here, the next we want to solve in this problem here, just seconds. So we want to solve 623. Okay, so if you go to 623, the question is talking about many chemical operators believe that the inerted vapors above a flammable liquid are not flammable when they mix with air. This is not true, by the way. They will say that it's an inert vapor. If it's above a flammable liquid, it's an inert vapor. How it could make a flammable mix with air? It does. This is frequently not the case. If the inerted vapor escapes from the vessel and mixes with air, or if the vessel is purged with air after emptying, the resulting mixture might be flammable. Okay. So, and especially when you think of inert, you think of nitrogen only. Yeah, for example, it could be carbon dioxide, it could be steam, so it could be something that's flammable, okay? A storage vessel contains liquid benzene at 100 degrees Fahrenheit. The vessel vapor space is inerted with pure nitrogen to a total pressure of ½ inch of water gauge. So this is my pressure. It is represented now in inch of water. It could be represented as millimeter of mercury. So this is just a unit. This is just a unit, okay? Assume that the vapor space is saturated with benzene vapor. A. Determine the volume percent concentration of benzene in the vapor. And of course, if we get the volume percentage of benzene in the vapor, now I can compare it with the flammability limits that I have. And then it says here, use a flammability diagram to show whether or not this mixture will become flammable when mixed with air. Here we will try to solve the problem using the flammability diagram as it's mentioned here. But first I need to find what? I need to find the volume percentage. So let's start solving 623. Okay, so 623. So what I need here is to find the volume percent. So this is what I want, is the volume percent. And to get the volume percent of benzene, okay, to get the volume percent of benzene, actually all what I need to know, and I can see that from the information that I have, if I take the partial pressure over the pressure that I have, the total pressure, is going to give me this fraction, and this fraction will just be my volume percent that I need. Okay, it will give me the fraction that can give me the volume percentage. Okay, so what I need here, I need to calculate the partial pressure, and I already have the total pressure here. So if you go back to the question, it gave me that it is at 100 degrees Fahrenheit, and it gave me that it is a total pressure of ½ inch of water gauge. Okay, so at 100 degree Fahrenheit, what will be the saturated vapor pressure? And in that case, so in that case, I can use the Antoine equation. So where it says that lim P sat, if you can recall, of course you already know that, which is A minus B over T plus C, and that is equal to 15.9008 minus 2788.51 divided by T minus 52.36. And in that case, I have T, which is 100 degrees Fahrenheit. Of course, I just need to put the right units here, which is 311 Kelvin. So that is the 100 degrees Fahrenheit, which is about 300 Kelvin. And if you substitute that, we are going to have the P sat will be equal to, the P saturated is going to be equal to 5.119. Okay, sorry, it's going to be 3.2 psi. It's going to be 3.2 psi. Now if I just want to divide this by the total pressure, okay, so what is my P total? My P total was the thing that I never heard about, which is the 0.5 inch of water, right? 0.5 inches of water. If you just need to do your unit conversion, this is 12 inch in feet, and then you put your PSI for every 34.4 feet of water. Okay, so this is just a unit conversion, and we are going to get the answer 0.0178 PSI absolute. Okay, so it's PSI absolute. So the total pressure, if I want to calculate that the total pressure here is not only 0.0178 PSI, actually I said that absolute, but I need to add this to 14.7. So the total pressure actually is equal to 14.7 plus 0.0178, which is equal to 14.7178. It's like 14.72 PSI absolute. Great. So now if I divide 13.2 over 14.72, this is what I said, like the partial pressure over the total pressure, I'm going to get the answer 0.217, and if I multiply this by 100, I'm going to get the 21.7% of benzene. Great. So I have now the 21.7% benzene, and if I want to calculate how much nitrogen I have, well, the nitrogen will just be 100%, the rest, right? Minus 21.7%, that will be 78.3%. So this is part of now solving the problem. So I just showed you of how to do my calculation here. Okay, I just showed you how to find the volume percentage. But what I need to do now, I need to show you the flammability diagram. And to do the flammability diagram, I need to remind you by the stages. So if we can recall that we have already taken the flammability diagram in our PowerPoint presentation. So that was our flammability diagram, which is problem 623. So if you want to just zoom in, I'm not sure if I can do this, it's better for you. So if you can recall, we already explained this, but now I have 3 lines. If you can remember, I have the stoichiometric line. Okay, so the stoichiometric line, I have the LOC line, and I have the air line. And on the air line, I'm going to identify my UFL and the LFL, if you can recall. Okay, so let's go with what? The stoichiometric line. Okay, the stoichiometric line. So what I have benzene. So benzene is C6H6. So if I want to do my balancing, which were C6H6 plus O2 gives us CO2 plus H2O. Okay, plus H2O. So the first thing I want to look at the hydrogen. We have 6 hydrogens, so I put 3 here. I have 6. A carbon is 6, so I put 6 here. So I have 6 carbon. The last thing I go for oxygen. I have 12, 15. And because I have 15, I will multiply here 15 over 2 into 2, so it's 15 oxygen. So it's 7.5. 7.0. So my Z is equal to 7.5. Okay. And what should I do to find out this thing here? This is how I do the stoichiometric line. Z over 1 over Z multiplied by 100. And if you do this, which is 7.5 over 8.5 multiplied by 100, this will be equal to 88.2%. Okay? So and that is the 88.2%. So if you go on the line of this oxygen line, 88.2%. So this is 88.2%, and then you go to the 0. So you'll have a line that goes like that. Okay, that's my line. Okay, beautiful. So I have drawn the first line that I have here. So let me select another color here, just to draw the second line. And my second line that I will try to do here is the LOC. So what is LOC? Yes, LOC is simple. You can get that from the table. And getting it from the table, and just to know, you just go table 6.3. Okay, where should I write? Okay, so table 6.3, I will get the LOC is what? LOC is equal to 11.4%. So we go here 11, so this is 0, this is 20, so this is 11.4%, and then we go parallel to this line here, parallel to this line. So I'm going parallel to that line down there. Okay, so I have an intersection here. Okay, so now the final line that I want is the airline. Okay, so this is my airline. What should I do with the airline? The airline, as you remember, that you go, it's like a fixed line from 0 to about 79%. So this is my airline. Let me select another color. What else do I have? Maybe orange is good. Okay, so that is my third line. Okay, great. So now I have 3 lines here, and remember that in that line I need to identify the UFL and the LFL, and my LFL is equal to 7.1%, and my UFL is equal to, sorry, my LFL is 1.4%, and my UFL is 7.1%. So if you find what is the LFL and EFL on this point, it will be somewhere here. I think the color here will not help me, so I'll select something like that. So it will be somewhere here, sorry, it will be somewhere here and somewhere here. Okay, so these are the 2 points. Now if you can recall, what did we say? We said that we can find the upper and the lower limits by going through what? By going through the limiting oxygen. The limiting oxygen concentration. And it is the one that identifies the flammability region. And what do I mean by that? Now, this is what I'm trying to do. I'll try just to draw my lines here. Unfortunately, it was green. The flammability region is green. Sorry for that. And here is this point here where I go from my limiting oxygen to the upper limit, hitting here, and then my limiting oxygen to the lower limit where it hits here. Okay, sorry, my lower limit was down there. Oh my god, oh my god. Okay. Can I take this off? Okay, I took 2 lines off. Okay, I took the stoichiometric line off. So it was there. Yes, that's the one. That was the lower one. And here I'm getting what? I'm getting my flammability region. I got my flammability zone. Now if I want to see that after I have drawn my flammability diagram, I just want to make sure that is it flammable or not. We have 21.7% benzene and 78.3 nitrogen, and if you're going to do that, this is 21 of the fuel, which is benzene, and that is 78.3 somewhere here. So this is the line, and you can see the line here passes through the flammability limit. Passes through the flammability limit. That means at a certain amount of oxygen, at a certain amount of oxygen, I could have that on the flammability, in the flammability region, and it could be flammable. You see? So we are saying that it could be flammable, and we are discovering that is possible even with an inert. Beautiful, right? So that was for the question 623. That was a very beautiful question to go through, and it was a good example that you can learn from how to use the flammability diagrams. So now we will try to solve 627, and I wish that I solved 627 before, because it shows how we do calculate the volume percentage. We already did now, so we already should be knowing that. So what is 627? The following liquids are stored at a storage vessel at 1 atmospheric pressure and 25 degrees centigrade. The vessels are vented with air. Determine whether the equilibrium vapor. Okay, equilibrium vapor. So I have the temperature, I can calculate the saturated pressure and so on. Above the liquid, so the equilibrium vapor above the liquid, using of course the saturated vapor pressure, will be flammable or not. Okay, how can I know that's flammable? So at 25 degrees, I'm going to find Psat, and after I find Psat, I divided it by 1 atmospheric pressure, the total pressure. I will get the volume percent. So what I'm going to find, Psat divided by total pressure, I get the volume percentage, and then I compare the volume percentage with the flammability limits at appendix B, and I will know that if it's flammable or not. So I think so that is a straightforward problem. So we go now to 627. That is 627. And the procedure, I think so it's a good idea that I already write a procedure here, because I have explained this several times. So the first thing I want to do is what? I'm going to use the Antoine equation. Okay, I'm going to use the Antoine equation. Where do I get the values of A, B, and C? I get them from appendix E, appendix A. Why I use the Antoine equation? To find Psat. Okay, to find Psat. And this is the equation where we say what? We say lim Psat. Okay, if you can recall this, lim Psat is equal to A plus or plus B over T plus C. So in this case, let me write it. So this is like A plus B over T plus C. Okay, so that is the equation. So and then you're going to find what? You're going to find Psat. Okay, Psat. What is number 2? Number 2, you're going to use Dalton's law. Dalton's law, and here in Dalton's law, why? To find the volume percentage. Okay, the volume percentage concentration in air. Okay, great. So how do I find that? I find it using that equation. Well, volume percentage is equal to Psat divided by P total that I have multiplied by 100, and I'm going to get the answer. Great. So here, what do I find? I'm going to find my volume percentage. Now for number 3, then what you're going to do, if it is flammable or not, you're going to compare with the flammability limits. We are going to compare with the flammability limits. Where we can find these? We find them in appendix B. Why do we do this? To know if it is flammable or not, to find that if it is flammable or not. Okay, so this is what we are trying to do. So these are the 3 steps, and now let's apply the steps here. So we are going to select the first one, and the first example was for acetone. So the first thing, acetone from appendix E, I have a lim Psat. Lim Psat is equal to A, which is 16.6513 minus B, which is 2940.46 over C, T plus C, which is minus 35.93 with T. And we already have T, which is 298 Kelvin, right? It's already given by the problem. It's 298 Kelvin. And by that, I'm going to find Psat is equal to 228.4 millimeter mercury. And always be careful with the units, by the way. And the volume percentage is going to be 228.4 divided by the total pressure, which was 1 atmospheric pressure, which is 760 millimeter mercury, and that will be 30.1%. And now if I go 30.1%, I say, okay, what is appendix B? What does it tell me? Appendix B tells me that the UFL is equal to 12.8%, and my LFL is equal to well, I think so that is good enough, right? Because if I have the upper limit is 12.8, so the lower is going to be lower. And what do I have here? I have 30.1%, which is above the upper flammability limit. So definitely it is what? It is not flammable. It is not flammable. As we said, we have a lower flammability limit and upper flammability limit. Between them, it is flammable. However, here above that it is not flammable, and below that it is not flammable. Okay, so we just need to be careful that we should remember those kind of concepts. Okay, so that was so that was for 42627. I know you can do this by your own, or I can keep it part of the assignment, but we got an idea of how we can solve this problem. Great. Now let's go to our next problem. Our next problem will be 630. Great. So what is 630 about? You have decided to purchase a 500 gallons tank of liquid propane to heat your house. Okay, so you have a 500 gallon tank to heat your house during winter. You are concerned about the tank rupture. So if my tank ruptured, I have a crack, and the possibility of a vapor cloud explosion of propane is formed. How far away in feet must the tank be away from the house to ensure that your house will receive no damage, not even a minor damage, from the explosion? And when we talk about minor damage, we're talking about shatters of glasses, windows, and so on, right? So the specific gravity of liquid propane is 0.5. The energy of explosion of propane is 488.3 kilocalories per gram mole. Okay, so if you recall what we have taken already, so what it is asking us here, we are saying that's minor damage. So we need to know what is minor damage here, and if you go in table 69 and find out what is minor damage, is about talking about 0.7 psi. Okay, so the first thing here, I'm going to write 630. So my minor damage, I'm talking about P naught is equal to P naught is equal to 0.7 psi. Well, now if you just think of your calculation, okay, what is my aim? I have now this information. What is my goal? I want to find R. How far away? Okay, I want to find R. So if I have P naught, so if you can recall what I used to say, that start with what damage you're expecting to find the P naught, and then from P naught I want to get PS. Why? Because as I get PS, I can find ZE from the figure, and ZE is equal to, if you can recall, it is equal to the R divided by M TNT to the power third, and so I can find this R here. Okay, so I have it in mind. Well, this is MTNT. Do I have MTNT, or if I have the other M, which is the mass of propane, which means that I need to work on the equation which says that the mass TNT into the E TNT is equal to the nu into the mass of propane, in this case, into the delta heat of combustion, or the energy of explosion for propane, which is already given to me. So as we have, this is given to us, and this is given to us, and we can say that this is open, and we are going to consider the value of 0.05. And we already know ETNT, we can calculate MTNT, right? And then we substitute here MTNT, and what we will have, we already have ZE, and we can calculate R. I think so our problem is very clear here, and we can go on and start solving our problem. Great. So what I'm going to start with, I'm going to start just putting the information that I have. I have now 500 gallons. Okay, 500 gallons, 10. Okay, 500 gallons of propane. There's a lot of unit conversion here that we need. What else I have? I know that's the molecular weight of C3H8 for propane is going to be 44. I have the specific gravity where I can get the density, which is equal to 0.5. My energy of explosion of whatever you call it, that is equal to 480.3 into kilocalories per mole. Okay, and now by all that information, I think so I can substitute. Okay, I don't have the mass, by the way, right? I don't have the mass, but since I have the volume and I have the specific gravity, I can calculate my mass. Okay, and this is not really a trick, rather than that it tells you that in real life not everything is given to you, you need to calculate it. So mass is equal to what's going on here. Mass is equal to the 500 gallon, and I multiply this by the specific gravity. Of course I need to multiply by the density, 62.4 pound mass per feet cube, and just doing the conversion for the gallons here, so 1.1337 feet cube per gallon, and the answer here is going to be 2086 pound mass of propane. Okay, so I already have now the mass of propane very beautifully. If you want to take this into kilograms, this is about 946 kilograms. Okay, so just a conversion. I did it. I found now the mass of propane. So what did I find? I found this term here. So if I put that in blue, okay, sorry for that. So I found mass. I already have delta heat. Well, is delta heat of the combustion, or the energy of explosion, is good for me? Well, it is in kilocalories. It's in kilocalories per mole. So and actually I have it per kilogram. Maybe I need to do some kind of a conversion here. Either I convert this kilogram to moles, or I do my molecular weight here and have this in kilograms, kilocalories per kilogram. Whatever you do, it is fine, as long as you find whatever you want. But maybe we already have the 946 kilograms, so we are going to continue and say that just take it to moles, doing your conversion, and this is going to be 21,500 moles. Okay, now this is ready for us. So we have now the right hand side. I have here, I do have 0.05 multiplied by MP, which is 21,500, multiplied by delta heat. I already have it here, so I can see it here. It's 488. My God, that's not clear. Okay, I did that with the blue one. So that will be now 488.3 kilocalories. Okay, so that is like in kilocalories. So now I have all this right hand side, and my ET&T, I need now my ET&T in calories, and if you just can recall, that is 1,120 calories per gram. So I'm going to write it 1,220 calories per gram, and note that here it is in grams. Okay, so there is always tricky things that you need to make sure that you have your right conversion. Since it's in grams, my MT&T is going to be appearing later in grams. Okay, so if you solve for this, if you solve for it, the only unknown that we have for MT&T is the mass of TNT, the equivalent mass of TNT, which will be 4.69 to 10 to the power 5. That is that much grams of TNT. Great. So what did we say? We wanted to get this MT&T. Why? If you go back, we wanted to get this so we can substitute it here. Why? Because we want to get R, and R is equal to what? ZE into MT&T. So now we have the mass of TNT. We only need to get ZE. How to get ZE? We need the scaled pressure. So we can get the scaled distance from the scaled pressure by the figure. How to get the scaled pressure? We get it if we know the overpressure, and we get this overpressure from table 6.9. Okay, we can get that from table 6.9. Well, we don't have any damage to our house. Okay, so going down there, we just need to calculate now our the pressure values. So the pressure values, what we have, we already have that this equation PS is equal to P naught over the ambient temperature, and we said that it is 0.7 psi and the ambient will be 14.7 psi, which is equal to 0.0476. And then using the figure here, if you use the figure, which figure is it? I'm going to write the name of the number of the figure, figure 623. So using figure 623, we are going to get the ZE is equal to 33 mass per kilogram to the power 1/3. And here I just can calculate my R distance, and that's it. I do my calculation, which is 33 multiplied by 469 kilograms of TNT, and this will be equal to 251 meters, which is equal to 824 feet. Great. And how beautiful, you can see that I already identified that it should be about 250 meters away to say that I'm safe if there's any rupture, and that propane that I'm using for heating my home. Okay, things are beautiful when you get the feel of how you can do these calculations. Great. So that was for 630. We have also a few problems that we will try to solve here. We have 631 and 634, 44 and 45. Let's see what we can solve from them. The last problem that we are going to solve here is 634, and I think so that will be good enough to cover all the ideas that we need in this chapter. So in 634 it says you have been assigned the task of assisting in relocating the new control room for your process. The new control room will be designed to withstand an explosive overpressure of 2 psi gauge. So you have the damage here, right? Oh, sorry, the overpressure of 2 psi gauge. It should be able to withstand this pressure. Your attention is focused on a propane storage tank located 100 meters away from the proposed size from the new control room. So the propane storage tank is 100 meters away. What is the maximum quantity of propane in kilogram? So we are talking about the maximum quantity of kilogram that can be stored in this tank without exceeding the overpressure rating of the control room, without exceeding the 2 psi of the control room. Make sure to state any assumptions. So what do we have here? We have the R term, we have the overpressure term, but what is the problem is asking us to find? It is asking us to find the mass. The mass, where is that? It was here. What is the maximum quantity of propane? So we need the mass of propane. So if I can calculate from knowing the overpressure and knowing the R, I can calculate the mass of TNT. And if I calculate the mass of TNT, I can calculate the equivalent mass that will be in propane. That is the solution of the problem. Okay, so it is straightforward. So we go to 634, and I'm going to start directly solving the problem. We already have P naught is equal to 2 psi, and just to calculate now PS, which is P naught over PA, that is 2 divided by 14 divided by 14.7, that will be equal to 0.136. And now using the figure, okay, I'm just doing this quickly because you already have the idea now. Now using figure 623, I can get ZE, which is equal to 11 meter per kilogram to the power third. So I have 11 ZE, and now because I have ZE, I can calculate the equivalent MTNT, and my equivalent MTNT will be equal to, of course, here's to the power third. MT23 is equal to R divided by ZE, which is equal to 100 meters, divided by 11 meter per kilogram to the power third. the answer is going to be 9.091. However, this is what? This is not the mass. We need to find mTNT, not the power third. We need to get the power third. So this will be 9.09 to the power 3, and the answer will be 751 kilograms of TNT. Now I have the mass of TNT. All what I need to do is to find out that relationship. If you can recall, mTNT into ETNT is equal to nu, it's equal to nu into the mass of propane into the delta heat of combustion. Okay, so what do I have here? I have mass of TNT, I have heat of TNT. This is what is mu now? 0.05 or 1? Okay, it's open. We are talking about outside the control room. So mu is going to be 0.05. Okay, let's continue. This is actually what we want, is the mass. The delta heat of combustion, we can get it from Appendix B. And here the delta heat of combustion from Appendix B, we can find that it is equal to 2043.1 kilojoules per mole. Okay, we just need to consider here that it is kilojoules per mole, so we need to select something that is satisfying. So if it is per mole, we need to make sure that this is now not per mole, right? So we want that in kilogram. The answer will be in moles if we keep that there. This also should be kilojoules per mole. No, that mNT that we have is 751 kilograms. So my ETNT should be what? My ETNT should also be per kilogram. So I'm just making sure that the units, they make up well together. So I need the molecular weights to do part of my calculation here. So if I do my calculation with the unit conversion, my mass is going to be equal to 700 kilograms of TNT. Okay, and I'm going to multiply this with 4686, that is ETNT. Okay, 4686 kilojoules per kilogram. So I selected the one that has per kilogram. Okay, just to make sure that the units are good. This is the mu or nu, and that is multiplied by 2043.1 kilojoules per mole, and that is multiplied by or divided by the molecular weight, which is 0.044 kilograms per mole. Okay, now with all this conversion fixed up, I will get the answer to be 1516 kilograms propane. Okay, so that is about 1 ton. I mean, and that is not really a lot. That is possible amount. And of course, I already selected the mu to be 0.05. But if you're going to have a different efficiency of nu, problems are going to be different. Imagine now I said 0.05. If it's going to be higher, this mass will be lower. Okay, this mass will be even less. Okay, so this is the amount that I would expect. This is the amount that I would expect that will cause to me that overpressure that I have, the overpressure which was 0.7 psi. Okay, and sorry, that it was 2 psi. Now that was 634. That was a very beautiful question, and that was the final question for today. For this chapter, you will be given how to solve 644 and maybe 645. They are very beautiful problems. Again, 45 is talking about the propane, and 644 is also talking about some other compound here. Just to get an idea, so 644 says a lab worker has left an open beaker, right, 1.5 liters of carbon disulfide on the desk in his lab office at the end of the workday. So it's open. He forgot it, and he closed his office door when he left. To save energy, the company turns off the office ventilation system. So the ACs are off, or sorry, the ventilation system is off at the end of the workday. So what will happen? CS2 will accumulate. It will evaporate because there's no AC, and it will accumulate. It might be that it causes a cloud or a flammable mixture in air, and an explosion might result if the worker turns the light switch on. Boom. Okay? The temperature is 30 degrees and the ambient pressure is 1 atmospheric pressure. The floor area of the room is 3 by 3 meters and the ceiling height is 3 meters. So now you know the volume of this place here, right? And you know that it is in a lab, it's closed, so our new value is not 0.05, it is 1. Okay, so I'm just giving you the ideas. Okay, so estimate the resulting concentration in volume percentage. So if you can get the PSAT value, or I don't think so that you need the PSAT value. Actually, what you need here is we already have the volume, the total volume, and we have the volume also of that CS2, right? We already have an idea about the volume here, and if you want to get an idea about the volume, what do we have? We have 1.5 liters here, and from the 1.5 liters you can know how many moles do you have, right? And if you know how many moles do you have, you already can use PV is equal to nRT to calculate what volume of CS2 will be in that room. Okay, so considering that all of it evaporated, so we already have that. It already says that it evaporates. Okay, so all of it evaporates, so we know the number of moles, and using PV is equal to nRT we can find the volume of CS2, and if we divide it by the total volume, in which we already have the volume here, 3 by 3 by 3, right? And which is 27 meter cube. So we can find the volume percent of CS2. Finding the volume percent is really important because we need to compare if it exceeds the flammability limit, the lower flammability limit or not, which we can find in Appendix B. Okay. Now, after we have found the volume percentage and compare the flammability limit, now what is the equivalent amount of this TNT from the vapor when we have an explosion? So we need to see the delta heat of combustion, of course, and we see what is the equivalent amount of TNT there, just to get a feel of what kind of explosion or what amount of energy that I'm going to get out of that. If the vapor explodes, at what distance is the 3 psi over pressure found? And you're going to find that 3 psi is very large, is dangerous, and then you're going to find at what distance, which is the R value. If you find the R value, imagine that person sitting there. How dangerous is that going to be for that person? Is it going to be dangerous or not? Find out. Okay, so that was for 644. So you'll try to solve that by yourself. Going back to 645. So you have our plant site wishes to install a pressure vessel containing a total of 1000 propane. Again, very similar. We are concerned about the scenario of the rupture of the vessel and subsequent mixing with air and explosion of the flammable mixture. Our control room has a maximum side of overpressure of 3 psi, so it can withstand that. How far in meters must the vessel be located from the control room? So this is very, very similar to the example that we just have solved, so I don't think so we need to explain that. That's very clear. And then how far in meters is the R value, where it should be located in order to have no more than minor damage to the house structures. So you're talking about some houses, no minor damage to the house structures. So go to table 6.9 and find out what is that pressure of having no minor damage to the house structures, and based on which you're going to calculate all the other values to find R. I think that I clarified that good enough. Until then, I think so we are up with this chapter number 6. It was a very good chapter. It took a lot of effort from myself and yourself, and I hope that you have gained a lot from that. You're going to use this information a lot, at least for your life, and not only in industry. when you think of how fires happen around you. An industry, you need to consider all the possible flammability limits that could be causing a real dangerous situation when you are in the industry on site. I think so you feel more confident now about safety when you studied all the chapters that we have taken so far about the threshold limit values, about the flammability limits, about what effect could it have to the surroundings from houses, or the steel that is within the house, or the people who could have some damage in their ear, or the people who could have some kind of death because of lung hemorrhage. It is something, it is a knowledge that not everyone can have, but you have it now. So use it for the best and use it for the good of mankind. Thank you very much and wish you all the best. Master.